Hi everyone, this is Frankie. I'm doing my project on sustainable steel making, specifically the molten oxide electrolysis process. Uh, that is currently being led by the company Boston Steel. So let's get into it. The first thing I want to start out with is that the whole reason this project has been gaining traction is that it's trying to mitigate the effects, or well, the negative environmental and, I would like to think the human effects of the metal industry right now. So we're going to focus on specifically iron and steel, since steel is a primarily iron-based alloy. So right here, we're going to start talking about those specific effects. So this is an open pit mine. I feel like most people have seen this before, but if we're going to analyze exactly what's going on, is we see that there's a lot of land degradation, and it's not using the land as a renewable resource, but rather as a single use sort of. Once you've mined the area, you're going to have to really rebuild that area to gain any use from it. So we have that. We also have large amounts of waste. So all of the mining waste gathers, and then we have to figure out what to do with it. We also have, if there's any underground operations, we have unstable or sinking ground. There's air pollution. There's, what do you call it? Sort of leaching, industrial leaching from certain processes, especially if there's water running through the area, and then you uncover certain old human underground operations or other geological forms under the surface. We're also consuming, if we're talking about the processing of these metals, it's using the consumption of non-renewable resources, which we'll get into later, and greenhouse gas emission, which again we'll get into later. And then, of course, if we're talking about worker hazards and rights, we would like to mitigate those as well. So we're going to go over, as an extension of that, some statistics surrounding iron and steel in the US specifically. A lot of these are from the US Geological Survey. So this year, this is from their 2024 report, so it's mostly 2023 figures. We have 93 million tons of steel consumption the past year, 19.5 billion total purchases of iron and steel scrap. Recycling 1 ton of steel saves 1 ton of iron ore, 0.6 tons of coking coal. Coking coal, it's a type of processed coal that is used in the processing of iron ore, and 0.05 tons of quicklime. So we'll get into what that's used for also. 2 tons of carbon dioxide are produced for every ton of steel produced, and the steel industry is anticipated to grow by 30% by 2050. So we have a lot of these huge numbers surrounding consumption, and that means that we are continually causing these types of processes. There is a lot of steel recycling, or iron and steel recycling in the US, but we still want to lessen the effects because they still generate greenhouse gases. So we went through that. So we're going to talk about the most traditional form of purifying iron ore. So we're going to use magnetite, which is a type of iron oxide. That's going to be right here. The coke that I mentioned earlier, and then the quicklime. So the blast furnace also refers to the fact that hot air is being blasted in, and that reacts with the carbon, and that creates our CO right here. This is the net reaction. So there's a couple processes that happen before that, but then here we have the magnetite, and then we have heat in the blast furnace, and then that creates what we want, right? The pure iron, but then it also generates CO2. So it's emitting huge amounts of greenhouse gases. And I think this is one of the interesting things, is that a lot of the environmental movement is surrounded around plastic, when we don't even consider the cost of processing certain things such as metals, which, of course, if we have metal waste, it doesn't leach into the environment like microplastics would, but it does have a huge impact in how much we need to process and mine it. We have the human cost, we have the environmental cost. So this is what Boston Steel is trying to sort of counter in the metal industry. So here we have traditionally what happens. Here's the hot air goes into the furnace, and so in the electrolysis process, we also have this vessel where we have here we go. Yeah, the iron coming out, and then we also generate slag. So we actually I'm sorry, I misspoke. In the Boston Steel process, a lot of, because it's an electrolysis process, it says that it has very little waste. So in here, that's another thing to think about, is that we have a lot of slag, which is what the quicklime, oh my gosh, I didn't even explain the quicklime, is to remove the impurities in here in the iron ore. So when you think about this process, which by the way has more steps than the Boston Steel process, we have to not only source but also process this carbon into coke. We have to source the lime, and then it generates greenhouse gases. So that's why it's not really a viable long-term method. Okay, so here's Boston Metal, Boston Steel. Yeah, it was built off of the MIT researcher Donald Sadoway's work. So he started this the research surrounding this process. It was patented in 2014. They have one location in Boston and one in Brazil, but unfortunately, they're still in pretty early stages. They don't have the process commercialized yet. So even though in the scientific community they've gained a lot of traction for what they've been doing, it hasn't actually hit the industrial commercial level yet. So this is what I was going to say, is that this is not really it's not as new as it kind of seems to be. This is the process it was based off of, processing aluminum oxides to get pure aluminum. So that process was built upon, and this is now the running operation for this company. They call it molten oxide electrolysis. It goes by different names, but I'm just going to call it MOE. So at a very high temperature, they have this entire, well, like we said in class, redox reaction process. We have an inner anode, and we have the iron ore coming in. We have a electrical current coming through this cell that has the electrolyte to allow the electrical current to pass. What happens is that the iron gets heated and pools at the bottom, and it purifies. Oh yeah, here we go. This is the net reaction, so we're going to go back here. And as we can see, the oxygen gets to leave a very environmentally safe byproduct. Very few industrial processes have only oxygen as a byproduct. So, yes, this is the entire process. So there's the ore, and then the molten iron comes out. It doesn't show it here, but there should be a tube to let it escape. Then there's just what we were saying about in class about cells. So this is the net reaction. So if we take hematite, for example, which is a mineral that contains, it's an iron oxide, and then we add an electrical current, we're reducing that iron oxide, and we have our pure iron here, and then we have our oxygen byproduct over here. Oh yes, and so this is what the company is saying, is that it can take industrial waste over here, and then we have scrap metal, recycled metal in the form of steel. We have iron ore over here still, and so all of these sources can be processed by the MOE process that Boston Steel is leading. So to kind of summarize this whole thing, I want to talk about the viability of this project. There's a lot of pros. Obviously, streamlined processing. They want to expand this method into other forms of metal processing, primarily oxides, obviously because of the process that we just explained. And then not only that, but also creating different alloys of steel. We already mentioned it uses a renewable energy source, the electricity. We don't need that coke, the processed coal. We don't need that anymore. We don't need the lime. We don't need water. We don't need hot, well, water, yes, but not every single time we process. It's going to be the cell with the electrolytes in it. So turns industrial waste from liability to profitability. So industrial waste is such a huge issue for several reasons. Obviously, liability, environmental concern, human concern, but also just physical. It's a physical stress on a company, where to put it. So if we can get more profit out of that waste, that's going to be good for the environment and good for the company. So this is more of the same, gaining more from scrap, recycled metals. Another thing that they like to say is that they have a modular, transportable design that can be scaled up and down for whatever operation it is being used for. There's some cons though. Obviously, it has huge electrical demands. It consumes 25,000 amperes and for one commercial unit. It's still in the beginning stages. We're not sure if it'll hold up over time. There's a lot of controversy over whether those inert anodes can really hold up for that long, because it's just such a new process in terms of large-scale commercial iron ore processing. It's also difficult to implement in the current industry when there's such a huge standard that's been held up for a long time. That's a large issue with a lot of processing of any sort of industrial processing, mining, such as that. So yes, and then also the anode degradation that I mentioned. So here are my references. I hope that was informative, and yep, that's it.